Okay, good afternoon. Good day to everyone. So for classes that do not fall in the afternoon, but right now we are having this afternoon class, this last session of Physics 2, and thank you a while ago, for Barbie, in leading us in prayer. Is Edward Escorpiso already in the class? I think he's the only one that is not yet checked, in our attendance. And I do hope, that he can join us this afternoon. So we will have a lengthy discussion. But for our discussion this afternoon, we will go into the reading assignment I give you, from pages 70 of your textbook up to page 80. So far, we are still in this number of pages. Our goal is to be able to exhaust the the book that we bought. So you just get your book recently, last week. And our goal is to really maximize the use of that book. Now, however, guys, I will emphasize that we will not limit our idea to the things that we learn from the textbook. We will probably realize that if we will do that, the author of the book is usually focus into some topics that they would want to emphasize, and maybe the things that you want probably to learn, you may not really be able to get it if you have only one reference material. So if you want to really exhaust the knowledge of the certain topic, you can get other references. So that's a way of balancing out what this author understands and what is this author's teaching you versus other experts that are also there. Now, however, uh, for our convenience, of course, we adopted a specific textbook. But again, it does not limit us in reading, in understanding the topic that is set or given to us, so that it can widen also our perception, our understanding. Now, right now, the topic that we will be discussing, and we will relate this to the previous lesson that we have. And previously, we come across our discussion on electrostatics. And I know you understand it, The word electrostatic comes or will probably mean that we are dealing with charges that are at rest. Now, charges that are at rest are basically very different from Unit 2, because in Unit 2, we will now make these charges, if we are able to have or have a storage of them in huge quantity, we will let them move. And of course, they can move whenever we provide them with a path. So the charges will be given a conductor, a wire. So we will have now the opposite of charges that are at rest to charges that are in motion. And commonly, when we deal with charges that are in motion, we are looking into this word called electric current. And electric current, if I'm going to give a definition, this is the rate of flow of electric charges. Now, there's the word there, rate of flow. And for rates of flow, it will always be in terms of some amount, whether they are in numbers. And then we always relate it with time. So, ano ang mga examples ng rate, speed, acceleration. These are rates, of motion. How fast, is an object running? How fast is it changing its speed? So those are what we call rates of flow, or movement. Now this one, we are dealing here with electric charges. Either electrons are considered, how many millions, how many thousands of electrons or charges are passing a given section per unit type. So here, between 2 points, we will see that a particular charge or charges are being transferred, or are transferring in location. Now, in our previous topic, we got to know that charges eventually move, no? They have this natural tendency which we call as their electric potential, no? Now, this electric potential, we describe it, no? That the electric potential of a charge, no, at a particular point is denoted by this variable V. Okay, so there's this variable V, no? And if we will get the unit of this electric potential, we encounter the unit volts. We shorten the unit by writing simply letter V. And if we will try to explain or to write the equivalent equation of V, we get to have work over charge. Or in symbol, we get to have the value W over Q. So this is what we have for letter V. So V is denoted by W over Q. Now, further transforming it, no, we can also write there work to be equivalent to VQ. So if you multiply the denominator with V, then you can get also the work there. Now, so it means that a particular charge is if we are able to move a charge, no, from one potential to the next potential, then we need to do some work on the charge Q. So that's the essence of electric potential, no? So you are able to move a charge, and therefore you are doing work on that charge. Now, I think, no, the one that is responsible in making it move is this quantity called electric potential. Again, no, the unit of this electric potential is volts. Now, there are times when we relate the value of the work, no, with energy, since they have a similar unit. They defined energy to be the capacity to do work. So we can simply intertwine or interchange the use of units for energy and work. No? That energy or electrical energy in this case can be written as V times Q. And I hope that you will recall that, no? Because we will relate it to later to another variable. Now, what does this mean? No? That 1 joule of work can be equivalent to 1 volt, no, of a particular number of coulombs of a charge. So 1 volt coulomb is equals to 1 joule of work or energy. Okay, so because our unit for work or energy is in joule. So this is it, no? So, or 1 volt can be written as 1 joule. So another way of writing V, which is W over Q, is that 1 volt is equals to 1 joule, no, 1J or over coulomb, no, or 1J over C. So that's our value volts. Now, when we provide a path, no, for our charge, guys, then that path is most definitely a conductor, no, or a wire, no. So the only way that your charge can move is that you will have, no, a conductor, no. So we have here a wire. This wire or conductor, no, will allow our charges to travel here, no. Without a path, the charge will never transfer or move, no. So you have to provide a path for that, no. Now there are some wirings that are small in area or diameter, but there are also wirings that have very big diameters. So they come in sizes because of their application. If you use them for heavy tasks, no, then maybe what you need is a wire that will also be bigger in dimension. So depende kung diin mo sila gamiton, no? Not all sizes of wire can be used in any kinds of application. As a matter of fact, no, I saw one phone that was an electrical phone wire. They kind of remove it, no, because it's old. And then since it's very long, they connected it to the electrical posts. They connected the wire there from the electrical post and bring it to their home. No? Now, the problem was when they start to switch on the appliances in their house. They noticed that that telephone wire that they used eventually caught fire, nasunog. And the fire produced was so fast. It runs very fast. They have no time to run after it or put it off. And then again, that's how fast is a fire developed by using the wrong kind of wiring. Now, March is the fire prevention month, and we are always reminded that we have to be very careful about the things that we use in our house. When we cook, I think the other week I heard over the news, a guy that cooks a meal, or cooks rice sa iya rice cooker, and unfortunate in unfortunate events happen that this rice cooker, I don't know, if that's the reason why their house was burned, but that's the only thing that he turned on before he left, just moments, and then when he get back, pwede nagaluto siya, that's it, the sunog na ilabalay, so I heard that over the news, over, I think that was last week, and it's a sad story, when your house gets burned, because of this wrong use of electrical appliances or the wrong use of wirings, because they are really they really pose danger when you use them incorrectly. Now again, these are the path where we provide for our charges. So we have conductors. Now our conductor or wiring, we use several types or several kinds of wire. Some people would use copper, and copper comes with a lot of advantage. They are affordable, they are commonly available, and then the kind of metal that defines copper is that copper is described to be ductile, or it has the property of ductility. And ductility, guys, anybody would like to explain what is meant by ductility? I think somebody was raising their hand. Joseph, can you explain to us what's the meaning of ductility? Yes, Joseph Taroha, go ahead.
Yes, sir. Ductility is the ability of a material to be drawn or plastically deformed without fracture, sir.
Okay, so ano ang keywords? What are the keywords for the word ductility? It is the property of a metal to be Okay, so it can be drawn, pwede siya butungon, it can be drawn into wires, So if you have a thick copper wire and you have this device called a die, so a die is some kind of a tool that you can pull. You can stretch it little by little until magniwang na nga magniwang ang wire kag maghimo na siya laba-laba ang wire. Now, question, are all metals ductile? Tanan ba lang ang metals ductile? Are they all ductile? Okay, can you repeat your answer?
Not all metal are ductile, sir, but most of them are.
Okay, thank you. So ductility again, may not be present in every metal, but I believe a great number of them are ductile. So you can pull them and then eventually they'll be turned into wirings. Now, other than copper, guys, so again, the word die here represents to a tool that we use to stretch the wire. Now, another type of material that we can probably use is as a conductor. Is your is our aluminum. No? So aluminum is also a good conductor. No? Advantage of aluminum is that it's very light. So even if you have to use longer lengths of the wire, no, they will not be very, very heavy. And then silver and gold are also used as a conductor because they don't corrode. No? They don't get, kung sa salsalon, parang nagatok-tok. No? They don't corrode. No? And usually when metals corrode, their conductivity is affected, that it cannot allow charges to travel anymore whenever they are corroded. No? So you have to clean it, no, so that the charges again are free to flow, no, between its terminals. No? But silver and gold is rarely, no, affected by corrosion. No? But I think copper and aluminum, they have that possibility because they are a little bit more cheaper. No? But we don't use silver and gold as ordinary wires, obviously, no, because they are expensive kinds of metals. Just imagine if you use a wire, no, and your house, no, is using copper or is using silver or gold as a wiring. Most likely, no, you will just open your house for burglary. No, people will just steal, no, those wirings in your house, no, because the wirings alone are very expensive. No, so again, no, some things about, no, a path for our current. No, now these conductors, ladies and gentlemen, no, they all have this thing called electrical. No, we have this thing we call as electric resistance, no, or electrical resistance. Whatever metal you have, they will always have this property to oppose the flow of charge. Tanana sila, no? But however, some metals have lesser tendency to oppose it. Other metals will have a greater tendency to oppose. No, you will observe that not all metals are really great conductors. Some of them are lesser, no, lesser in nature in terms of conducting. No, in one section, no, one answer of conductors, they gave an example of alloys. They gave examples of a bronze. But for me, bronze is a kind of a metal that is rather used for other applications. No. Now, I'm not sure if I've seen a bronze wire, no, but definitely bronze is used as a tool of firemen. No. So if you have a fireman, may bombero da, no, ang iyan nga wasay is made of bronze. No. And why is bronze specifically used sa iyang axe or sa iyang wasay? No? Because ang bronze never spark. No? Even if you hammer it, no, on the floor or on other metals, it will never spark. No? Or if ever it will spark, no, it will spark, no, the remotest possibility, no, nga mag-spark siya, no, gamay-gamay gid, no. So that's one characteristic of bronze. No? So it's safe to use, no, when you crack open somebody that is trapped in a car. No, maskin lampusan mo na kalampusan sang axe na nga bronze, no, hindi na siya mag-i-grab. No, it cannot create fire. No, so that's one characteristic of bronze. No, well, again, no, some other metals, no, maybe I'm not sure of bronze if it is used as a conductor, no, or a good conductor. No, but again, no, all conductors are, no, they always have this resistance. And the symbol that we use for electrical resistance, guys, so let's give it a symbol here. No, we denote a letter R, no, to denote for electrical resistance. And this electrical resistance will have a unit. No? So the unit of electrical resistance is known as ohm, OHM. Now, the person that was attributed it to, no, the guy who gave the unit ohm is George Simon Ohm. Some people will pronounce his name as George. Others would pronounce his name as Georg, no? So this is the guy, no? And I guess we've given a lot of units already, no? So, so we have ohm, and the symbol for ohm is the Greek symbol omega. So the omega symbol is something like this. And if the value of the resistance or ohm value is higher, then the more the wire no, will cause the charges to flow slower or more difficult. No? If the resistance is high or low, I mean, no? If the resistance is low, then the flow of the charges will be smoother, easier. No? So there is an effect no? Of the electrical resistance no, on how the charges are actually moving in the wire. No? Again, no, the smoother flow is an indication that there's less or lower resistance. A higher resistance would mean that the charges will be moving slower or that the wire will develop heat. Now, smaller wires usually, no, kung i-allow mo na ang damo-damo o charge, no, let's say 1 million or 20 million electrons. And then also here, no, 20 million electrons. I think the 20 million in the larger wire, there would be lesser no, struggle because they have a greater area to pass through. But the 20 million passing through this thinner wire, they will have a lot of difficulty. No? And maybe the wire here will heat up. Now, because of the slower motion of the charges here, then we say that this wire with lesser size has higher, no? It has higher resistance. Amo na ang tendency sang mga wire nga gagmay, no? Taas na ila resistance. Even though they are both copper, no? So this one will have a higher resistance because of its size, no? Ang iyang kadakuon. Then this one may have a lower or lesser resistance because of its dimension. No? So there are factors that affects resistance R. No? Again, no, the unit of that is ohm. Now, our value of R, ladies and gentlemen, is affected, no? Affected na siya kuno by length, no? So R is directly, no, proportional to length L, no? Sorry, length must be like this. And likewise, R is inversely, no? Kunang istorya nato ng iyang cross-sectional area, no? So it is inversely proportional to its area. No? Now, the area of the wire is this round thing. No? We call it as the cross-section. Now, if that cross-section is larger, then your wire no, will be, no, it will have a, what, no, a lower no, resistance. If the area there is wider. No? If the area is smaller like this one, then the resistance becomes higher. No? So something in the area of the cross-section that affects the resistance of the wire. No? So no? These are factors that affects the resistance of our wire. So we deal with the idea of current, no? And current, no, is the rate of the flow of our charge. How do you understand the word current? Anybody would like to try? Okay, or you can also explain how do you understand what is voltage. Pwede man, no? There are two things that I would like you to tell me, no? So there are, I think, no, one or two who raised their hand, no? Let's listen to Joseph. What would you want to give us a meaning to, no, Joseph? Current or voltage?
Para sa akin, sir, I use an analogy with a water tank, sir. In this analogy, charge is represented by the water amount, but the voltage, sir, can be represented by the pressure of the water pressure. Tapos, the current, sir, can be represented by the water flow, sir, of the water tank.
Okay, no, that's a wonderful analogy. No, we call it as the analogy because that's the closest thing that we can imagine. No, water and current. No, pressure and voltage. No, so what makes the water flow in the wire? There is a pressure or a force that pushes it. No, and again, according to Joseph, the voltage is the one that push the water, no? Or the current. No, and therefore the charges are flowing in the wire eventually. No? So that's a good explanation. No? Now, anybody else would like to try? Anyone would like to try to explain, no, other things that you understand about current or about voltage, no? What are your what do you think those terms mean, no? So but however, no, the explanation of Mr. Taroja is quite substantial, no? So something must push, no, the charges in the wire, no, and that one, no, is created by your voltage, no, or there must be a source for it, no, like a water tank, no. If there's water tank in your home, you have to fill it up with water, and once it is filled with water, then now water is steadily flowing in the pipe. Your pipe serves as the wiring, and the water there will be equivalent to your charge, no, or to your current. Now, here are chapters that we are expected to be encountering, no. So we already introduced the words electric current, electrical resistance, no. Then maybe, no, we will be combining some expressions and formulate eventually the principle called the Ohm's law. Now we will use this principle of the Ohm's law in trying to understand chapter 5, no. But our idea of a circuit was already, no, we have a bit of a glimpse, no, kung ano ni ang circuit dito sa aton discussion sa capacitor, no. In our discussion on capacitors, we were introduced already of the series and parallel connections, no. Now, just to get back a bit, no, on circuits, no. So for our circuit, guys, and this is a picture, by the way, of a circuit. Here is an image of a circuit, no, this one below, no, here. This is a picture of a circuit. So this connections of wirings is quite impossible for you to analyze, no, how many voltage, how much is the capacitance, no, if it looks and appears this way, no. We cannot understand or analyze it in this way. That's why, you know, there's always a need for us not to use the schematic diagram. Our schematic diagram is a flat two-dimensional drawing of our circuit components, no, and how the flow of charges are occurring in our circuit, no? And we saw that now when we discuss capacitors. So here we will have some symbols here, no? So schematic symbols are needed, and among the symbols that we already learned are that of capacitors, that of a battery. Now future symbols that we will still encounter, we will have our resistor, no? Which is having a unit also of resistance, no? So ohm na iya unit, no? Our capacitor has a unit in capacitance, farad, no? And our battery has a unit of the voltage, which is in volts. So all these components, no, plus maybe a switch and wirings, no, will now complete our schematic diagram, no. Now again, as a form of a symbol, we have the following. So capacitors are drawn in this way. They are drawn with two parallel lines, shorter parallel lines. Batteries are drawn in such a way that there is one long line and the other one is a short line. That's your battery. The resistor is drawn in this manner. It looks like a zigzag line. No? So if you encounter a circuit element that has zigzag line, this is called as a fixed resistor actually. So there's some kind of a zigzag line. Now you can add the word fixed, because it has one single value for the resistance. They call it fixed resistor. A switch will probably appear in this way. It is a line and then there is something like an opening and then there's another line here below. However, this one can be turned on and off. So you can move this up and down. And usually what they add there is a so you can switch it on and off. And a wiring is simply a straight line. So you can extend it to connect your elements. Now for our battery, there's a positive side to our battery. This longer side is the plus sign. And then this other side is your minus, negative side. Okay, so these are our schematic symbols when we deal with circuits. So electric circuits, when we close it or when we turn it on, okay, sometimes circuit is written as CKT. Now, an open circuit means that the circuit is switched off. You move the switch upward, so you open the circuit. No charge is moving in the wire. But when you turn it on or you close it, you now let the charges flow in the wire. So we will be dealing with a lot of this circuitry over this side. And as what I've said earlier, you are to study the circuit construction kit found in your FET simulator. It's called as Circuit Construction Kit AC. So there's a lot to learn there. So what I want you to know is that there are ways to measure voltages, currents, and we have tools there called ammeter, voltmeter, that you have to know how to use. So you have to check this one. And I think the link is provided as well. Now, your capacitor is this orange one. And this one is your resistor. These are the fixed resistor. Now, these huge ones are your capacitor, guys. And I'm not seeing any battery here. But I believe there are other elements there that provides the energy for this circuit. Now, that's the circuit that we have. Terms like resistance, electrical current, electric current and electrical resistance, and they are quite important in the use or in the functions of our circuitry. So every conductor, tanan gid nga electrical conductor, they always have this thing called resistance, R. All wires, maybe some wires are better conductors than others, therefore their resistance is lesser, but definitely all of them will have resistance. And one factor that affects resistance aside from length and cross-sectional area is temperature. They notice that when wires are hot, they develop this thing like a like an increase in temperature. Increase in temperature causes the resistance to go higher. There's a higher number of ohmic value or ohm value in the wire when it is hot. That's why some devices like computers, They have to put it in an aircon room to lower down the temperature. So in a way, it's like a coolant, no? The aircon. It cools the device so that it will not compute, no, erroneously, or hindi magsala-sala ang solves ang imo computer, no? Because again, no, of the higher resistance in the wirings and its components. So temperature is affecting, no, the value of the resistance. And again, the resistance is the opposition, no, or the difficulty of charges to flow freely, no, in the wire. Now, again, no, when we combine current and resistance, you eventually have your circuit. But where does the charges come from? No? Where do we see these charges coming from? Now, we see them coming from a possible battery. And here is a picture of our battery. No? So the source of our charges comes from this battery. Now, Alessandro Volta, I think, no, was the one guy that develops the battery, no, the electric cell. No? Now, what they observed was when you have a battery, guys, and you put a wiring, no, across its terminal, the charges eventually flow here. No? Now, this one is merely an illustration that charges eventually flow. No? But in reality or in practical situations or in real life, never attempt to put, no, wirings across the terminals of your battery because you may get burned. No? Mapaso ka gina, no? Kaya you will create a short circuit, and that short circuit will cause the wire to melt, no? And no, eventually it can burn you. So, however, no, as an illustration here, when we provide a path, the electrons in your wire, no, will now have the possibility to flow. No? So ano ang pag-flow ng electron? Electron flow will travel from the negative side and it will proceed to the positive side of the battery. No? So malibot na sa, no? Since my wire, then the electrons will now flow in this manner. I will represent the electron with this letter E and a minus sign above it. No? Now, you will notice, however, that the current, no, if we are to draw a current, the current moves in the other direction. Now, going back to the electron first, no, why will the electron travel from the negative to the positive side? Now, it is explained in our electric potential discussion that a negative charge or an electron will always travel from lower potential to higher, no, potential. Ang aton nga negative end, amo ni ang lower potential sa aton battery, ang positive end amo na ang higher potential. So ang electron amo na ang iya movement, no? However, when they use, no, some methods of calculating this, no, and they were able to develop in time, no, the idea of a current, they thought the current, no, is going from positive to negative. Amo ni ilaya nga initial gid nga idea sang current, no, that currents travel from positive to negative side, no, and they made a lot of computations, and then they denote the current here to be letter I, no. When the idea of the electron came out, no, nga ang electron galit travels from negative to positive, so it now created a confusion. Now they were more accustomed to the use of the flow, no, from positive to negative. Kagang ilang ang mga equations, no, parang they will have a similar answer. They have to agree, no, that this must be the flow, no. This must be the flow of the current, no. So our current, guys, is important, no. Its direction is important for coming up, no, with similar answers, with exactly the same answers, no. So if I am an expert in the Philippines and there are experts in another country, they come up, no, with a convention or an agreed direction of the current, and that is from positive to the negative side. Do you follow? So which one are we using in our computation? The current direction or the electron direction? Again, no, we are using the current, no, as a unit, no, in most of our computation. We never use electrons, no, in computing, no, values in our circuit. So so the importance of knowing, no, the idea of our current I. So current, no, again, is moving from positive to the negative side. And this is how the current, guys, no, this is how the battery, I mean, no, would probably appear. No, this is how the battery would appear. No, this is a diagram of solution there. No, so maybe, no, let's use a different electrolyte in this case. No, so let's say I have sodium chloride. No, so table salt. I will dissolve it in some water. No, I create a solution. So a teaspoon or a spoonful of sodium, no, sodium chloride, I melt it, no, or I dissolve it, no, in water, in tap water, or in distilled water. Now, what happens is that our electrolyte now will dissociate in this liquid. So what I mean by dissociation, its ions, no, sodium ions and chlorine ions will now float in our liquid. So there would be positive sodium ions and negative chlorine ions, no, that will be floating in the liquid there and will now gather themselves, no, if you're going to put these electrodes. So these electrodes will now collect, no, one of these two ions. Now I think, no, the ion that is positive is known as cations. So these are the positive ones. And then the negative ones are known the anions. No? They are known as the anions. So these ions now will collect in one of the two electrodes. So our electrodes will either be a positive electrode. No? The positive electrode is known as anode. And the negative electrode is known as the cathode. So they will now gather in one of these two electrodes. And once they now collect themselves, no, in one of the electrodes here, an electric field will now be set up. Since one is positive, no, ang mga charges, and then the other one is negative ang charges, then now, no, an electric field is set up, and then therefore charge will flow in the wire, and therefore the bulb will now light up. No, so masiga na niyang bulb karon, no, because of the electric field and the current that is now able to travel in the wire above. Now, the liquid below can be similar to our battery now, no? Because it's supplying the circuit above with a steady flow of charges. So amo na niyang charge karon. No? So a battery is a useful device to be able not to provide charges, no, in our circuit. So again, no, that one happens because of what do you mean that by that? No, that one happens because of the creation of the ions, no, that is floating in water. No? Okay, so any question? The word for our sodium chloride here is known as the electrolyte. And there are other types of electrolytes. You can use an acid, no, like sulfuric acid. You can put some drops of sulfuric acid in water, no? And then therefore that sulfuric acid will also dissociate into ions, and it can also, no, become like your battery, no? Okay, so I think in some car batteries they use sulfuric acid there, no, in the plates of the battery. So if you're familiar with your car batteries, no, that's a wet cell. So it is something like this, no, but there are already several compartments there, no, in your car battery, no, but there's a solution that they put there, no, maybe sulfuric acid, no, is one, no. And then therefore, no, that allows the charges to be developed because of the electric field created in the plates, no, inside, no, your car battery. So what we have here is probably a conductor, a wire, no. There are several things that we can look into this wiring, no. One is there is a cross section, no. We'll see that there's a cross section over here, no. Now a cross sectional area, no, is how big is the opening of this tube or this wiring, no. So this black part here is known as the cross sectional area. Now if you have a wider area, you can probably call it A, no. And then you could also have another factor here, no, for this wire, no, its length. And these two factors affect your resistance actually, no. So R, according to our relationship, no. So the resistance R is affected by some value K, no, KL over A. And KL over A is actually, no, your K is your resistivity value. L is the length, no. So if you have a longer length na wire, its resistance would be higher. But if the cross-sectional area is smaller, then you will have lesser resistance. No, I mean, if the area is wider, no, you have a lesser resistance. Now this value K over here is known as the resistivity of the wire. And resistivity is a property of the wire, no. Its number of ohms, no, for every unit of length. And there are symbols that uses instead of K, others would use the symbol rho, no, to denote resistivity, no. Ang resistivity it looks like this, no. Ang iyang rho symbol or rho representation, no. Now, usually since a lot of symbols are using K, they use this one instead for resistivity, no. And in our next video, probably we will see some listings of this resistivity value, no. So if we are to write the value of R eventually, our R, no, can now be written as rho, no, and then there's L, and then there's a denominator A below, no. But again, no, beside it is this Greek letter rho, something like letter P, which is known as your resistivity. Now this is how we determine the resistance, no, in our given wiring, no. So our wiring, no, may cause the charges to flow smoothly or more difficult, no. But again, no, as I've said, all wires will have a resistance, a value of resistance, no, all of them, no. Now there's a case where the resistance of the wire, no, is made minimal or actually zero, no. But it's not an ordinary or a phenomenon that is easy to achieve, no. There is a condition where you have to do, no, a lot of things, control a lot of things in the laboratory, no. Now the condition where we get the resistance to be zero is known as superconductivity. Okay, in this condition, or you have a conductor called a superconductor, this is when the resistance becomes zero, no. So there's no ohm value anymore in the wire, no. And I think, no, when you get a zero number of ohms in the wire, that it is good for communication, no, because there's no more difficulty for the charges to travel, no. So maybe, no, the sending of the communication will be quite very fast. No? Okay, so this is about your resistance. No? Now, just about somewhere below here now, we will see how the electrons are traveling, and I think I've already explained this now when I mentioned that electrons flow from negative to positive side, but the current is flowing from positive to the negative side. No, so this is just merely a reason why we have the explanation for our electric potential. So electrons no travel from the negative to the positive side, no, whereas the current no is the other direction, no, from positive to negative. Now we again no can measure the value of current no, in terms of Q over T. Now previously kaina, when we talk about electric potential, we were able to find that electrical energy is equals to VQ. No? So we have our value VQ, or 1 joule is equals to 1 volt per 1 volt coulomb. No? And this is what we give for our electrical energy equation kaina. No? Now, right now, what we have here is an equation for current, which is denoted by I, no? Being equals to Q over T, no? Or therefore 1 ampere of current, which is that unit of current, no? That 1 ampere is actually equals to 1 coulomb per second. No? So that's number of charge per unit time, no? Ang iya value. So ampere is our unit of current, and we denote I, no, for our current. Now from here, from I equals Q over T, we can also notice that Q can be written as I times T. No? That 1 coulomb can also be equivalent to 1 ampere, 1A, no? 1 ampere second. So that's also equivalent to a coulomb. No? So Q equals IT. But if energy is VQ and Q is IT, then we can also write here that energy E, no, can be written as V, since Q is IT. So we can write V times IT, no? Where again, no, E here is the electrical energy, and we can have here VI times the time. Okay, so again, no, this is still joules, no, ang aton unit, no. So electrical energy has a common unit of joule also, but in our homes we don't use joule because joule is too small. So for electrical energy, usually what is commonly heard as a unit is kilowatt hour. So have you heard of the word kilowatt hour? Can I see thumbs up for those who have heard of the word kilowatt hour? This is our common unit because kilowatt hour is quite larger quantity of energy. Kung joule aton gamiton sa aton balay, makalabot siguro sa millions na value. When in fact, now we only use no a small amount of kilowatt hour. No? But again, no, joule can still be used. No? Pero galing, we will have an enormous large answer. No? And usually our kilowatt hour, amunaya ang may amount. No? I think right now, pila bang aton per kilowatt hours? 11 pesos or 10 pesos. No? So that's how we assign our value of electrical energy. No? So how do we shorten the writing of the kilowatt hour? Sometimes we can write it as kWhr, no, to denote our kilowatt hour. No? Okay, so that's our equation. Okay, so I think now all of you are able to understand our lecture. No? So the video will be uploaded. No? And if you have no other questions, no, then we can call it a day. No? So that's just the discussion so far. We will add more no, explanation to what we have for this afternoon, no? So that you can better understand your work, no? So God bless, and see you everyone, no, in our next class, no?